Okay, dear students, very good morning to all of you. Yeah, we have got one lecture now on practical on testing of hypothesis and analysis of experimental data using R software. So we have with us Dr. B.N. Mandal, who is working as scientist at Design of Experiments Division of Indian Agricultural Statistics Research Institute. He joined the service in 2009, and since then he is working as scientist in this institute. He is also a faculty member in the discipline of agricultural statistics, and he has guided many students, MSc and PhD students in agricultural statistics. So as a series of lectures under this training program, we designed this particular class or particular lecture on this practical session on testing of hypothesis. Dr. Seema Jaggi, whatever has covered the theory portion, for that corresponding practicals will be done by Dr. Mandal. Also the analysis of experimental data, day before yesterday, whatever you had about experimental data analysis by Dr. Seema Jaggi, the corresponding practicals will be done by Dr. Mandal. So Dr. Mandal, I hand over to you for 1.5 hours.
Thank you, sir. Thank you very much. Good morning to all of you. It's my pleasure to take this class, which is a very important training program that you are attending. And I have been assigned the task of the testing of hypotheses and design of experiment analysis. The theory part is covered by Dr. Sumajaki, so I will be only focusing on the practical using the R software. I hope you are now familiar with the R software. So what I will do, I will directly take the practical part. So if you have any doubt in between while going on the practical, you can ask. So you stop at that moment and ask me what is the doubt you have. Okay, let us proceed. So I have prepared the certain exercises. So I directly open the R Studio. You can listen from you can hear. So because this is a practical session, so we all will be working in the R Studio. So please open up your R Studio, and I will be taking one problem at a time and doing the analysis. Can you read that line from there? Yes? From the last row. Can you read this line? Is it visible? Not visible. Okay, I didn't learn it. So little better? Or yet we need to zoom in more? So let us first deal with the test for single proportion. Okay, test for single proportion. That is the null hypothesis is given in problem. We have been given, say, portion P is equal to something. We have to test whether that is significant or not. Okay, so I have a problem here for you. In a sample of 1,000 people, 540 are rice eaters and the rest of the people are wheat eaters. Okay. In a sample of 1,000 people, 540 are the rice eaters and the rest of the people are wheat eaters. So can we assume that both rice and wheat are equally popular at 1% level of significance? That is the question that we are dealing with. Okay. So you see, now you have to understand this problem, and then you have to make it a test of hypothesis scenario. So there are 1,000 people here, and the data is being given that 540 of them are the rice eaters, and the rest of the people, they are the wheat eaters. So we find out whether the proportion of the rice eaters is equal to the proportion of the wheat eaters or not. Statistically, is it means the proportion is same or not? So you have to test that. Okay, so here because we can just simply we have only one sample of 1,000 people. and we can find out that 540 people are the rice eaters. So proportion of rice eaters is 540 divided by the 1000. So it is 0.54. That is the sample estimate. But significance of that, whether it is equal to the 0.5, or null hypothesis is that H naught small p is equal to 0.5, 50% or not. From the data it is 0.54. But we are testing the hypothesis whether the proportion is equal to 0.5 or not. Question is understood? Okay. Now how to do this test of hypothesis using R software? Okay. So here I have given that the n, small n, the sample size is 1000, and estimated proportion is p is equal to 0.5. So for testing this kind of hypothesis, a single proportion, the code that R, we can use the prop.test function, prop for proportion and dot test for testing. So prop.test x, it takes three commands. One is x, that is the number of success, and n, the number of trials, and the h naught, p is equal to p naught. What is the value of the p naught we are testing? That is the 0.5. And correct, that is whether we are making any small sample correction or not. So since this 1000 people is a big sample, so correction, there is no correction is needed, so correct is equal to false. So that will be the code, and if we run this code, did you follow the code? What are the inputs? This is the number of success, this is the number of trial, n. P is the probability, proportion of the people we are testing, that is whether it is equal to 0.5 or not, and then correct is equal to false. These are the inputs that you have to give to the command prop.test. Okay, so if you just run this line, this is just one line code, simple. So if you now let us see what result it gives. So this is the result that is coming. So one sample proportion test without continuity corrections. So 540 out of 1000 people, the data, that is null probability is 0.5 we are testing, and chi-square value is 6.4. So chi-square will come from the that is the proportion, estimated proportion minus the true proportion that we are testing, that square. Okay. And then so that is 6.4 value is coming with the degrees of freedom 1, and the p value is 0.1141. Okay. So all the results that come in the test of hypothesis in the R software, they will be giving the p value. Okay, p value will be the at what level that is significant. So this is the level the test is significant. That means now hypothesis will be rejected at this probability level. So beyond whatever this, so if we go for, suppose we used to make the inference at 5% level, then we have to check that p value with respect to 0.05. 5% means 5 by 100, so it is 0.05. So if it is smaller than 0.05, then it is significant at 5%. But if it is not so, then it is not significant. So our question was in the problem, we have been asked to that whether it is significant at 1% level or not. We have been asked at 1% level, not at 5%. So at 1% level, if we compare this p value with the 1% level, this one, so it is bigger than 1%, because 1% is 0.01, but it is 0.01141. So it is slightly bigger than the 0.01. So it is not significant at 1% level. That means the rice eaters equal to wheat eaters, that null hypothesis is not significant. That means null hypothesis is not rejected. It is not rejected. Not significant means not rejected. So they are equally popular at 1% level. But if we consider this at 5% level, the null hypothesis will be rejected. And at that scenario, at 5% level, their proportions are not equal. Okay? Did you follow? So at 5% level, if we say what is the inference, then the proportion of rice eater is not equal to proportion of wheat eaters. But at 1%, the proportion of rice eater is equal to the proportion of wheat eaters. Okay, so that is the, because of the level of significance, there will be two different kinds of inputs. So that's why it matters. The level of significance statistics is very, very important. Okay, any doubt here? So suppose similarly, if you are given some data on say any proportion data, so where you can estimate one proportion, and if you are asked to test the significance, suppose in the same question, if I ask you to test the null hypothesis that the true proportion is equal to 0.7, suppose if I ask that question, I can ask for this H0 is equal to P equal to say 0.7. So how do you test this then? You will change that P to 0.7. Rest of the data is same. Okay. You have to in that case change this to 0.7. This one. You change this part, not the other part. Okay, that is for single proportion. Now let us move ahead. Now testing for two proportions. When we have two different samples, independent samples, and we will estimate proportion in two samples, and we wish to test whether their proportion at the two different samples are equal or not. So that scenario. Example is here. Two batches of 30 cuttings from a certain plant, cuttings, each were subjected dipping treatment. There is certain solution at which the cuttings were dipped into at concentrations of 50 and 100 ppm. Okay, those two solutions were having concentration of 50 and 100 ppm of something, and the following proportions of rooted cuttings under each concentrations were obtained. So after dipping that cuttings, their roots grow in certain of the those cutting samples. So how many? What was the number of that thing? At 50 ppm, the proportion of rooted cutting was 0.5. So the solution where the concentration was 50 ppm, so 50% of that cutting grow roots, and at the concentration at 100 ppm, the proportion of was 0.37, 37%. So test whether the observed proportions are indicative of significant differences in the effect of the solution at two concentrations. So we have two different concentration of certain thing, and the rooted cuttings of 30 each were dipped into two solutions, and in first solution the roots grow at 50% of the cuttings, and at the second solution roots grew at the 37% of the cutting. So we have to test whether the two solutions, they were having the equal means equally giving the proportion of rooted cutting was same or not. That we have to test. This is the problem. So this is a test for two proportions, whether they are equal or not. Observed proportions are 0.5 and 0.37, but we wish to test whether this P1 equal to P2 or not. That is the null. Okay. So in this case, again the R command will be proportion dot test, and here because X is having because this is two sample scenario. So earlier only one sample scenario, number of success 540. Here two samples, so 30 total number of cuttings into 50%. So from the first sample, this is the number of success. From the second sample, 30 into 0.37. That is the second probably the number of successes, and the number of trials is 30-30. Okay, so that is the test. So proportion dot test X equal to because we have to, it is a vector, two terms are there, so within C we have to write 30 star 0.5 comma 30 star 0.37, and the bracket close, then comma N is C 30-30. Okay, because there are two samples, so you have to write like this. Did you follow? And you should be writing this thing, and you run this. If there is any error, you just tell me that properly you have to mention these things, because R is case sensitive. So while writing, you have to make sure that the case is proper, okay, properly written. If there is something capital N to write, or any bracket is left out, or if any comma is not given properly, your code will not work. If you want, you can take this code at the end of the my class, but you should still try, because you have to, ultimately when you will be analyzing your own data, you have to write. You will not get ready-made solution. So this is done by me, so I can share this file. There is no problem. But when you have your own data, you have to write your own code. So you just run this thing. So let us see the result. So this is a two sample test for equality of proportion with continuity correction is applied, because the number of samples are 30 only, very small. So it is not beyond 50 or 100. So that continuity correction, I have not made any faults like that. So this is the data, this is the chi-square and divisor of R, 1 again. So p-value is 0.4501. Now the p-value is 0.45. So if at 5% you wish to test the significance, are the that the proportions are similar or not? What will be the conclusion? Significant or not? Yes or no? How many are significant? Raise your hand. How many are for significant? And how many are saying that it is not significant? Not significant? 4, 5. Rest are significant? Now I do not know all of your names, but I would have asked my name. So what is your thinking? Is this test indicative of significance in the null hypothesis? Null hypothesis should be rejected or not? What is the conclusion? Significant. At what percent? At what percent level of this test is significant? Anyone? Anyone help us? Your friends will help you. So what do you think? At what percent level the test is significant? 1%. How many agree with you? The test will be significant at this value, at this value. So it is 0.45. So 0.45 is what percent level? What is the percentage? If you convert this to percentage, what will be the percentage? 45% it is significant. So if it is significant at 45%, will it be significant at 5%? No. Only at higher values it will be significant, not at lower values. So it will be significant at 45%, 46, 7 and beyond. Above 45%. It cannot be significant even at 10% also. Not 20%, not 30%. So these values indicate the value where it is significant. 45. Okay, now clear? Now let us move ahead. Now I am going through the t-test. But we want to test the equality of significance of means. So there are three kinds of t-test. One is single sample, one is two independent sample, and paired t-test. These are the three types of t-test. So first example is of, suppose this is an problem. An experiment was conducted to evaluate the effect of inoculation with mycorrhiza on the height growth of seedlings of Pinus cassia, some plant or something, I do not know exactly. If you are more aware about this. In the experiment, 10 seedlings, group 1, were inoculated with mycorrhiza, while another 10 seedlings, group 2, were left without inoculation with the microorganism. So there are two groups here. In the group 1, there were 10 seedlings. In the group 2, there were another 10 seedlings. In the group 1, mycorrhiza on the height growth of seedlings was the inoculation was made. But in the second one, no inoculation was made. Okay. So following table gives the height of the seedlings obtained under the two group of seedlings. So in the group 1 there was some treatment was given, that the inoculation was made. In the group 2 there was no inoculation made. And then height was recorded from the both the groups. So if you see, so these are the data. So from group 1 the height is 23, maybe I don't know what is the unit here. Whatever the unit, the same unit is there in both the samples. So 23 and 17 and so on. So there are 10 values here. And similarly for the group 2 there are 10 values. Okay. So from the group 1 heights were recorded, these are the heights, and from the group 2 heights were recorded and these are the heights. And both the samples are, of course, the plants were taken randomly. So that's why the assumptions are not violated. Now suppose we have to test that the mean height for the group of plants where the mycorrhiza was inoculated. Suppose we used to test that average height is say 25 for the first population. We do not think of the second population right now. Suppose we used to test that the average height for the first group of plant is says 25. That is our number. Mu equal to 25. H naught is mu equal to 25. So how do we go for the test? This is a single sample t-test. So you have to test this. You can do those calculations what madam has taught, x bar minus mu and so sigma upon root 10. So you can do that thing in yourself in Excel or some other way. But here we have, because we are doing through the software, we will not do each and every calculation by hand because ready-made things are ready. Okay, to make our things easier. But you can always check with yourself by doing the computations. So I have recorded this data in the form of vector, say H1, that means the height from the group 1, these are the values. Okay, height from the group 1, and H2 gives the height from the group 2. This is the values. Okay, this you may not type, but you can take it from me as well. So height from the group 1, height from the group 2, and the now code for, suppose I used to test that the first group, the average height is 25, say 25 centimeter. So t dot test, the command will be t dot test. Okay, in proportion it was prop dot test. In t test, the command is t dot test. Very simple command. T dot test h1, the variable for which you are testing the hypothesis. So h1, and you have to specify the mu equal to mu naught. What is the mu naught? Mu naught is 25. So mu is mu equal to 25. Okay, that is, so if you wish to test that it is mu equal to 30, you will make here 30. Whatever, depending on your data, whichever value you wish to test, you will write that value here. Okay, and whichever data you have to write here, data part. So let us first run this h1, h2, and then t dot test. So this is the result here. Now let us see the result. So one sample t test. See, this is one sample. Because we have considered only for the group 1. We have not right now taken the group 2. So t value is minus 5.2665. Degrees of freedom is 9 because you can see that in each group there are 10 slabs. So degrees of freedom is n minus 1, that is 9. P value is 0.005163, and alternative hypothesis true mean is not equal to 25 and so, and confidence interval and sample estimate 20.8 is the average from average height. So what will be our conclusion from this? So null hypothesis is rejected at that person level. So 0.001. So it is very highly significant even at 1% level also, isn't it? Okay. So that is the one sample t-test. Will you be able to do yourself now? So you have to just give the value of the sample, and then you have to call the t dot test, that vector which contains the values, and mu equal to 25 or whatever value you wish to test. Now for two samples, if we wish to test the hypothesis that mu1 equal to mu2, suppose we have two independent samples and wish to test that population mean from where these two samples were drawn, their means are equal, then we have to go for two independent sample t-tests. In this case, we have the two groups of plants and we wish to test that their population mean is equal. For the group 1 population mean, that is average height for the group 1 plants, is equal to average height for the group 2 plants. So that will be two independent sample t-test. Okay. And the command for R in R will be t dot test these two sample values h1 and h2, and we have to make that another input we have to give here, that is var dot equal. Now what is this one? Because in the t-test, if madam has taught you, I don't know, there is an assumption that the two population from where this two independent sample has been drawn, their variances should be equal. That is the assumption in the classical sample t-test. So that's why that var dot equal means variance of the two populations from which the two sample has been drawn, their variance are equal. That's why you have to write var dot equal to true. And true in capital always. True letter T, R, U, E, they will be all in capital. Because these are keywords, you cannot change that capital T, small r, you cannot change that. So you have to write always true or false, they have to be written always in capital letters. So this is the command, okay? T dot test H1, H2 and var dot equal to true. So let us run this code. So here's the result. So see two sample, now it is two sample. Two sample t test. Data is H1 and H2 and t value is 11.747. You compute and degrees of freedom is 10 plus 10 20 minus 2. So it is 80. Okay, 80 and this is the p value 7.107 E minus 10. What is E minus 10? Is 7.107 into 10 to the power minus 10. So it is very small value. So it is very highly significant as 1%. That means that the two populations have same mean that null hypothesis is rejected at very small level, even at 1% or 0.1% level. Very highly significant. That means two populations have average mean height is totally different. They are not same. Okay. Alright. So any question in this one sample and two sample t-test? Any doubts? Now let us proceed for paired t-test, because we have another t-test paired. So this is the problem. The following data pertain to organic carbon content measured at two different layers of a number of soil pits. So there are in a field there are soil pits. Soil pits means there are some pits there, and the organic carbon content were measured from that soil. So the examples are from different pits, from agriculture, from biology, and these are real data. These are not booked data. They are from some real experiments or real studies. Okay, so test whether the mean carbon content from two layers of soil pit differ or not. So there are two different depth layers of soil, because soil pits when measured there are layers. So this layer and then below layer. So different layers are there. So in layer 1 and layer 2, the organic carbon contents were measured. So this is the data. Say from layer 1, these are the measurements. From layer 2, these are the measurements. Okay, this is the layer 2, these are the measurements. Layer 1, these are the measurements. And the difference of measurement is this. So we have to test, and because this in the same soil pit you are measuring, the depths are only different, but the soil pit is same. So that's why the observations are paired. That means this recording, suppose for any particular value, it is low. So this is for the same soil pit. It is not that they are two different soil pits. So they are related. They are not independent samples. That's why they will be paired tests. Okay, for example, suppose if you take the blood glucose measurement before meal and after meal. So on meal you are measuring. So it is related. I am the person. So in that scenario, suppose I take the blood glucose measurement from all the candidates before meal and after meal. So if there will be two observations from each candidate. So the observations are paired. So in that case, that is the paired t-test we have to use. So similar is the scenario here. So if you make a, now we have to test whether the organic carbon content at the two layers are same or not. So this is not a case of independent t-test. It will be paired t-test. So for paired t-test, again you have to just read the data. So I have given the name OC1 from organic carbon from layer 1. You can give this name anything, X, Y, whatever you want. And OC2 is the organic carbon from the layer 2. So these are the values and these are the values. Okay, this is clear? I think this is good. Now for the command will be t.test OC1, OC2. that is x and y, and paired equal to true. This is the extra argument that you have to give the command. Okay, paired equal to true. Then only it will test a paired. Otherwise, it will be making a independent two sample test. The commands are very short and very easy. So you have to just remember this. So you have to give the values, sample values x, y, and the paired equal to true. That is the command. Okay, paired test. Now let us run this. And then so this is the result. You can see. So paired test. Now it is not two sample. It is writing. It is writing paired because I have made paired is true. So t value is 1.48. Degrees of freedom is 9. T value is 0.1718. So at 17% level, it is single, around 17%. So at 5% level, we can reject or accept. Reject or accept. Now, madam, is significant at 5% or not? Yes or no? No. Because it is 17%. 17 and higher values it will be significant. 17, 18. So below 17 it is not significant. So even 16% it is not significant. So 15, 14, whatever values are below, it is not significant at that values. So null hypothesis is not rejected. This null hypothesis cannot be rejected. That means the organic carbon content at two layers are statistically same. They are not different. Not rejected means what? Null hypothesis is accepted. We have no evidence to reject the null hypothesis. That means two layers have almost similar level of organic carbon content. That is the concept. Now let us move for any doubts so far? So these are the tests that I have brought only with me. Proportion, single proportion, two sample proportions, and the t-test, three kinds of t-test. These are commonly used. There are many other kinds of tests also, but they are not used that much. Now we will move to the experimental design. So Adam has taught about the distinct experimental design also. Which designs he has taught? CRT, RTD, and Latin square. Anything else? No. And you are aware up to how much? Before this training, okay, before this training you know up to CRT, RTD. Anything else beyond this do you know? Factorial and
lattice.
Lattice. Anything else? Augment. So ignore it. So here I have up to CRD and RBD, but of course we can quickly go into LSD and other things provided I have time. So you don't need it. So let us go for example of CRD analysis. So this is the example. So 10 varieties of which are grown in 3 plots each, and the following yields in kg per hectare are obtained. So there are 10 varieties here, and they are grown in 3 plots each. That means these varieties are grown in 3 plots each of the varieties. So, and this is using a CRD, completely randomized design. There is no blocking was done. So this is the data recorded. That is yield are recorded. These are the yield data kg per hectare. Okay. So variety 1, this may not be real data. So 7 kg per hectare. Smaller. So these are the data. 3 plots. For the first variety, observations are 7, 8, and 7. Okay. Similarly, for each of the data has been arranged like this, because when you record from the field, the plots will be at random, and units will be applied, treatments will be applied to the plots at random. So from plot 1 may be treatment number 3 for the recording. From plot 2 may be treatment number 2 for the recording. Then you have to arrange this variety wise or whatever treatment wise. So this is after arranging the data, these are the data. Now we have what is the problem? Problem is test the significance between the mean variety yield. This is the problem. So we have to say whether the average variety yield is same or not. Because we have 10 varieties, whether the average yield of all the 10 varieties they are equal or not. That is the problem. We have to conclude based on after doing the analysis whether the average yield of the 10 varieties they are same or not. So here you take the data first into R. So you will create a vector like this yield. So I have taken the like in rows wise. So I have taken the first row first, 7, 7, 14 up to here. Then the second row values, all has to be separated by commas. You know now this thing already you have done like this. And then the third row I have taken this. So the yield vector contains all these 30 observations, 10 from each, 3 from each variety. So now variety. So we have to create another variable that is called variety. So here, because this data is arranged like this, so variety wise, variety 1 to 10, isn't it? So here 1 to 10, first 10 observations are from variety 1 to 10, again next 10 observations are from variety 1 to 10, and again the last 10 observations are from variety 1 to 10. Okay, this way data has been arranged. That means if I wish to clear like this. So you have first the variety column, and then you have the yield. Okay, so because we have variety like 1 to up to 10, and then again 1 to 10, and then okay, 1 to 10. So whatever from the first plot, that is the value. From the second, likewise this. Again from here, so likewise we have arranged. So yield column is the rows where the yield from first 1 to 10, then again the next 10 observation from 1 to 10, and then the from again 1 to 10. So because these are from variety 1 to 10, I have written that variety here 1 to 10. Okay, because the first 10 observations they are from variety 1 to 10. Next 10 observations they are again from 1 to 10, and the last 10 observations they are again from variety 1 to 10. That's it. Okay. Because if you arrange differently, then the observation should pertain to particular thing that you specify correctly. If there is incorrectly done, that is then the inference will be wrong and the analysis will go wrong. Okay, so let us here. So this is the yield, and then you have the variety. So I'll show you how it looks. So suppose this is yield. So these are the yield values, right? And then variety, V-A-R-I-T-Y. Variety. So corresponding values of the variety. So this is from variety 1, first plot 7, from variety 2 7, from variety 3 14, likewise. And whenever we are doing any analysis for say ANOVA, any ANOVA or design of experiment analysis, the treatment factors, suppose treatments or blocks or rows and columns, the factors has to be converted into factors. So here our varieties are the treatment, so we have to convert them to factor. That is add. So this is done by using this command. It is very important. If you miss this line, your ANOVA will not be proper. Okay. So variety is equal to as dot factor variety. So that will be a factor variable. That is a factor variable. It is not, they are just not numbers. One, we are writing here variety number 1, but it is not a number. It is something. Say treatment 1. That is treatment 1 is something maybe. This is variety 1. Treatment 1 is what? It is variety number 1. So it is not a number. It is a factor. Similarly, these 10 varieties are the 10 treatments. But if you write like T1, T2 or V1, V2, then you may not write that as not factor, because strings, characters are by default taken as factors in the R studio. But for safer side, you can write that variety is equal to as dot factor variety. Okay, this you have to always do. If you don't do this, your analysis will be wrong. So yield variety and variety output factor. Now this is the command. The function that you use is LM. LM is for linear model. Linear model. L for linear, M for model. Linear model yield based on the variety. And yield is the dependent variable, the variable which you are analyzing. And what is the factor variable on the right side, that is the variety. And this symbol is the differential between dependent and the right side variables. So yield based on the dependent on the variety variables. So this is the command, and you can simply run this, but if you run this command like this, only this part, the result will not be stored anymore. So that's why I have created an object here to store the result. So that's why result 1 I am writing. Result 1 is the variable where I am storing the analysis result. So let us run this. So in the result object, this is stored. Now analysis results are here already. So now we can always access this thing, what is there. So after that, get the ANOVA table, we will use the command ANOVA, small a n o v a, ANOVA, or analysis of variance. And this works for the any linear model fitted object. So because result 1 contains the linear model fitted objects, so ANOVA result 1. ANOVA of result 1 will give the analysis of variance from that. So this is the outcome of that ANOVA. Now let us see the ANOVA table. So response is yield. There are degrees of freedom, sum of square, mean square, and F value, and the P value. This is also P value. Okay. So we have only one source of variation, that is variety, and rest is error, residual. So I have not done this line. I have not made that factor. That's the see, if you do not convert that factor, so I have written there. I have to run this thing. This line I have not run. That's why it is showing degrees of freedom 1. It is not 1, it is 9. So I have to run this line. So see, if you don't make that factor, this will be the problem. I have to run this. Run this. So run it, and again you can run this, and then this is the correct ANOVA table. So 9 now. Okay. That's why factor is important. Don't make it factor, it will take as only one variable. So 9, this is the sum of square, mean square, F value, P value, and residual 20, because total 30, the total degrees of freedom is 29. So, and this is the sum of square declarer, mean square declarer. And what is the meaning of this triple star? Triple star is here. So it is significant between 0 and 0.001. Okay. And if it was suppose 1 star, you will see between 0.1 to 0.5. And if it is 2 star, it will be between this and this. Okay, accordingly you have to understand. So from this ANOVA table, we can see that the variety effects are highly significant because it is the code is between 0 to 0.001. This one, 3 star is there, so this is here. This value lies between 0 to 0.001 because it is 4.87 into 10 to the power minus 5. So it is very less than the 1%. Okay, so the variety effects are highly significant. So our null hypothesis was that the average variety yield are equal, and alternate was any two varieties at least has different average yield. So what is our conclusion now? Null hypothesis rejected at 1% level. So at 1% level we can definitely say that average variety yields are different. Okay, they are not same. That is our conclusion. Okay. So will you be able to do? Follow? Any questions? Any doubts? Doubts है तो मैं चला जाऊँगा फिर इससे पूछेंगे. Provided you are doing this kind of thing, I don't know which background or you are from, because your training is on genomics and so maybe you are from molecular biology or something like that. But since the lecture is there, so maybe some students is there. Okay, so main command is this thing. One is you have to write the variables first. You have to create the factor, the appropriate, and the LM model, and 4-5 lines. Now if you want to suppose now we have now seen that the variety effects are significant. So if we want to make a pairwise comparison, which treatment is the best treatment? Which variety is the best? We have to make a pairwise comparison. We know the varieties and then you get. So how to do that? For that you have to use something, some package you have to use. Now R packages come into there because many things in R, in the base version of R, they are not directly available. We have to use add-on modules, like they are called R packages. So Agricola is such a package which will have these facilities, which allows you to many kind of this extra analysis can be done, such as the least significant difference or the CD value, critical difference of the two treatments that can be computed. Many other analysis can be computed. Okay, so we have to install these packages. Always we have to install. It is not by default installed. So Agricola package has to be installed. So here to install any package, you know how to install a package? Yes, so very good. So let us see whether Agricola is there or not. If it is there, we did not install. But if it is not there, so I have to install. So AG is not there. See, because we have A fine, then AE, then AS. So AG, because the packages are alphabetically arranged. So Agricola is not there. It is not installed. So you have to install it. Install, agree. And for installation, you need net connection. Then you need to install from that CRAN server. Or alternatively, if you do not have net connection, you download the package from the net connected computer, take the zip file and install from local. That is another way. But if you have net connection, directly you can install. Okay. Nowadays net is there with everyone, or at least in every lab. So you can only. So this is installed now here. So then after installing, installation has to be done only once. Once you install, it is available for the lifetime in this system. In any system, if you install a package, it will be now available for all the. It is there now. So you have to just load this package. You can check this box here, or you can use a command for library. Library, name of the package. So library Agricola. Now so we will load this package. So library Agricola. It is running. Okay, see, now it is automatically checked. I have not checked this thing because I have run the library command, so it has checked this. That means this is loaded now. All the functions available inside this are available. You can see the details of the functions available in a package from here. You go to this, and there are lot many functions here. Many kinds of analysis extra things are there. So I am using only for this purpose that we want to do a pairwise comparison. We want to use lsd.test function. This is available inside Agricola. So lsd.test takes the input of fitted linear model object, so result 1 in our case, and the among which we want to compare. We want to compare the varieties. Okay, and that has to be made inside the quotes. Inside the quotes. You see the quote is there here. So it is to be written inside quotes and console equal to true. The result will be displayed here, provided if you write console equal to true. If you don't write this thing, the result will not display. The function, the author of this function has written like this, so you have to write this thing. Okay, so we run this and see the result. So this is the lsd.test output. The mean square error, these are the variety means, these columns, standard error. This is standard error column, this is the R replication for each varieties. Lower confidence limit, upper confidence limit of the means, minimum, maximum. But which we want is the this thing, LSD value. This is the LSD value. Least significant difference, 2.487. So that means any two varieties which have the average yield difference more than 2.487, that will be, those two varieties will be highly significant, different from one another, significantly different from one another. So suppose you have two varieties and you have the average yield. If you take the difference of that average yield, if that value is greater than the LSD value, then those two varieties have significantly different average yield. Okay, that is the interpretation. So using that approach, the software calculates and gives this result, this thing. So here variety number 3 is having the highest yield. Okay, and it is having letter A. Variety number 9 is having 11.33 average yield, that is having letter B, and so on. Now here, what is the interpretation of A, B, C? Interpretation is that any two varieties, if they have same letter in common, any letter in common, they are not significantly different. If they do not have, if they have some common letter, they are not significantly different. And if they have no letters in common, then they are significantly different. At least, if there is at least one letter in common, so they are at par, they are at similar level. But if they do not have any letter in common, then they are significantly different. So here we have only one letter each. Sometimes A, B, C. In single variety there may be 2-3 letters. So you could check all the letters with others. A is there only for the variety number 3, and nowhere A is there. So A is significantly different from all other varieties. Okay, and it is having the highest yield. So treatment of variety number 3 is the best variety out of this data. Out of this data, based on this data. Okay, so this is the interpretation. And variety number 6 to 1, they are statistically at par because they are in the same data. So they are in the lower side. Their average yield is lowest. Statistically 1 to 6 variety, they are at the same level. 3 is the best one. And 9 to variety number 5, 9, 7, 4, 8, 8, 5, they are having the again at par. The average yield is at par.
So what is the interpretation if we get a variety as AP? What would be the interpretation if we get one variety with the superseded AP?
AP. Suppose it was having AB. So B is there here and B is also there in this. So this variety will be at par with this because letter is common.
Both the groups.
Yeah. Any two varieties having common letter means they are at par. Alright? So the command lsd.test, that is useful for pairwise counting. And that will come from the Agricola package. You have to install. This is the takeaway from this. Okay, this is for CRD. Alright, any doubt here? You have to follow the CRD, then you will be able to follow RCPD and others. They are similar. If you follow the one example here, all other things, their commands are almost same. There is very little difference. So understand the first one. If you understand the first one, or the RCPD or the mean square, the commands are almost same. There is no different command. These are the same set of commands are using again. Only little, just one difference. So understand this properly. Any doubt you can ask me right now. Okay, let us proceed. So this is RCPD. So in order to select suitable tree species for fuel fodder and timber. So in order to select suitable tree species for fuel fodder and timber, an experiment was conducted in a randomized complete block design with 10 different tree species and 4 replications. So there were 10 different tree species were taken in the experiment and 4 replications were taken. The purpose was to select which tree species is best for fuel, fodder and timber production. So in this experiment, 3 species are the treatment. So the plant height was recorded in centimeter. So these are the tree species number 1 to 10, column 1, and the replication wise values. So for replication 1, these are the values. For replication 2, these are the values. For replication 3, these are the values, and replication 4, these are the values. So this is an RCPD example. The replications are the block. So blocking has been done, and within each block, each of the treatment has been applied once. So that's why it's RCPD. nice complete block design, and we have to see whether the tree species are significantly different or not with respect to, of course, width and height character. The character may be anything, the data will be similar. So the purpose is to illustrate how to do the analysis. So how do we go for the analysis? Okay. Example is clear. So now this data I have in an Excel file, because I have not recorded this in the form of data. So I will show this data. This one is the data. So this is the data. Okay. The tree, see, tree 1 to 10, the replication 1, the column 1, that replication 1 values here. You see this column 1 is this value. This one, replication 1. Then data has to be arranged like this. First column is for treatment, second for replication, third for height. Columns can be interchanged, but whenever the tree number 1, replication number 1, that and the height is there. So accordingly you have to arrange. So there will be 3 columns in RCBT analysis. One for the treatment, one for the block, one for the character. So again for replication 2, these are the values, and for replication 3, these are the values, and replication 4, these are the values. Okay. Treatment number 1 to 10, replication 4, and the values. Similarly for treatment number 1 to 10, replication 3, and so on. So data has to be arranged like this for doing the analysis. Clear? Because unless you arrange the data in this way, in 3 columns, the analysis will not be always it is columnar format. Now we have to read this data into R. You know how to read the data in R? Okay, I hope you know. So because this is an Excel file, so we have to read this file from that. So I can directly read. One way is you can read from here. That import data set command you can make use of. So that is from Excel or by code. That code is also there. Browse and go to the location here and select the file. So and the name of the data set that you want to give, because in my code I have given the name D2. Okay, so I will change the name here. Name I will be changing to D2. This name I can change on this. That was the file name. I will change the name as D2. And we have to see whether first row has the names or not. I have the first row has tree and replication, so names are there. So I will check that and open data viewer. I don't want it. So and you can see the data here also. So import. Okay, so data is imported. You can see it from this side. Yeah. Okay, so tree, replication, height. So data is there. Okay. Now after importing the data, this is the by code you can also import the read Excel command from the library using the read Excel package. So this is also by code you can read. So that is another issue. Now after reading the data, this part is not done. So I have done from that name. This part is done. You need not separately do it again. Okay. Now D2. Now because the data set you see here that the tree is numeric. It is showing that data is numeric. Replication is also numeric. Height is also numeric. But as I said, in design of experiment, you have to convert to factors. The treatments and the factors you have to convert as factors. So here the treatments are tree species and the replications are also the factor. So you have to convert them to factors. So for converting to the factors at one go within the D2, so within D2 object, because the replication tree and other things are within D2. So within command D2, comma, and you will put a curly bracket here. Tree is factor of tree, or as dot factor also you can write. Rep is equal to factor of rep. Okay, they are converted to factors, and there is no comma here. So tree factor and replication also factor. So within G2 now you see they are numeric. After I run this line, they will be converted to factors. So run this. Yeah, so now they have converted to factor. Right side you can see. Okay, they are converted to factors now. So after factor, now the command is again for this one. This is clear. Factor conversion, because I am converting within the data set. Earlier I have the CRD example. I have directly written the variety and here. It was directly in the global environment. Okay, it was not within a data set. Now this tree and replication, they are within G2. That's why I am converting them using within command and set it again in the name of the G2. So within G2 they will be converted to fact. Now for RCBD analysis, again the LM command, the variable which we are analyzing, the character, tree, treatments and the replication. Now extra thing in RCBD is this. One is treatment and another is block or replication. So tree is our treatment and replications are block. So tree plus replication, and where these are available? They are available from data G2. Okay, whatever the data object is. Okay, so this is the common. That is the difference with the CRD, nothing else. For replication, we have just plus that extra variable is there, and plus does not mean addition. It is just in the model there is extra component. First was treatment in the CRD case. In the RCBD case, there is block also. Block effect is also there. That's why tree plus replications and data set G2. So, and we have given the name result2 here. So let's run this. And after that, ANOVA command again same, ANOVA of result2, this is the output. ANOVA. Now let us see the ANOVA table. Okay. Here is the output. So you can see there are 10 tree species. So degrees of freedom for tree will be 9. That is 9. And there are 4 applications. So degrees of freedom is 3. If you do not convert this factor, it will come here as 1. It will also come here as 1. Okay, that's why unless you do that thing, it will come 1, 1. So be very careful. And sum square for treatment and block, and mean square x value p values. Okay, so from here you can see from this p value, because we are interested in the treatment also always. So here there are 3 star, or you can see the value also. From this value it is very clear that the treatment effects or the tree effects are highly significant. Okay, even at 1% also. So that means the average height for all the 10 tree species which are being used in this experiment, they have different average height. Okay, that is the conclusion, right? And for comparison, which one is the best? Again, we have to make that post lsd.test. It is the same command, there is nothing different. Same command, and let us run this. And we can see. So this is the now we have the common type of letter. See, now we have A, B, C, C, D, C, D. So multiple letters are there. So here, for example, B, C and C, D. So these two are having, though they have C letters common. Here also C is common. So treatment tree number 4, tree number 1, tree number 2. They are all at par. They have almost average height statistical. And similar, and on species number 6 is having the highest average height, because it is having letter A, and none of these other 3 species have the letter A. Okay. So this is the conclusion. Alright. So CRD and RCBD codes are similar. Now, any doubt here in RCBD? Any doubts? Will you be able to follow this? Code will be available to you. I will share the file, and here you can take. So that is not problem, but you understand what is being done and how it is being done. Time is also over almost. So I believe now this is for RCBD. If there is no doubt, so for if it is suppose list rapid square design. So another factor will be there, rows and columns. the CRT, no extra nuisance factor, only treatment. In the RCBD, treatment plus block. In the Latin square treatment, rows and columns. They are arranged in rows and columns. So there is treatment, rows and columns. So for that, only thing that will be different here is here after tree plus row plus column, there is extra thing will come. Okay, that is the difference and nothing else. All other things are like similar. Okay, you save the result, say result 3 and over result 3, LSC dot result 2, whatever is the treatment factor that will be. Okay, so that is the difference. And if it is factorial, somebody say factorial also you are used to. So factorial, suppose you have 2 factor or 3 factor, so there will be interaction also. So in that case, in factorial scenarios, the command is like this and like here. Where n, suppose y is the response variable, and suppose you have factor, suppose NPK, let us say nitrogen, say plus phosphorus plus say potassium. These are 3 factors of fertilizers plus their interaction. So N colon P, interaction between N and P, plus whichever interaction you want to take, N colon K plus E colon K. So these are the all 2 factor interaction. Now there will be another 3 factor also, plus N colon E colon K, and all of these should be factors beforehand. I am only writing the linear model command, but all of them has to be converted as factor every time. Then automatically interactions will also come as factors. This thing has to be made factor beforehand. Okay. So this is for factorial experiment. You will save the result, say in some object, maybe say result 4, and then you can write again ANOVA and those things. All the other commands will be similar. Okay. This is for factorial. Yes, similar. Okay. So I think this is and for augmented design and something else say. So augmented block designs, I think you were telling. Augmented block designs are incomplete block designs. So there is little. This is also block design example. This is complete RCBD randomized complete block design. So this tree is the treatment. These are the blocks. So in case of augmented block design, the here tree and the command is like similar, but there will be here for ANOVA table there is a type 3 sum square series, adjusted sum square series. Here the sum square are type 1 sum square, so you will not understand what is that. The sum square, the total of treatment sum square plus block and plus error sum square is equal to total sum square. But when there is incompleteness, the total of treatment sum square plus block sum square plus error sum square is not equal to total sum square. There is some adjustment in there. So for that there is a type 3 sum square is here. So special class of ANOVA is required for that. So there is another ANOVA command, that is capital A, NOVA is there, but it is not available in the base R. For this there is a package that you have to use. That package name is car package. Okay, car package you use. CAR. Car means companion to applied regression. That is car. Car is not that car. So car package, you have this command, and there you have this ANOVA. So that you have to use. If you are doing that kind of analysis, this is for your information. Okay, so this is all I have. Now I will be reading. Any doubt if you have, you can tell. I am giving this notes for you. Here you can take it from your editor. Okay. List of significance in R, and this fine. And I think I have given manual also. The manual also, you have the examples. Okay. Not the same examples, but there is examples. So this one I am giving test. Can take this code and hit it apply. Fine. Okay. So you are from which backgrounds? What are your backgrounds? I think mostly from the molecular biology or what? What are your backgrounds? Agricultural science, biological science, which disciplines you are? Genetics and statistics. Statistics also. Who are from statistics? One, two. Computer. Biotechnology. Bioinformatics is also there. So I think I should leave now. Alright. Thank you.